Hello everyone. Today, as a team of 7, we are going to show you the experimental setup of Darcy's law. So before we get into the experimental part, I would like to give you a very brief introduction about Henry Darcy. What has he done and his contribution to the hydraulic engineering field, and then we'll look into the mathematical equation and the components in it. So let's go. Henry Darcy was a French engineer born in Dijon, a town in France. Him being an engineer, especially interested in the hydraulic engineering field, designed his very own freshwater supply system for the town of Dijon in early 1820s. And he also served as the chief director for the water and pavement in Paris at around late 1840s, to be precise 1848. And at 1856, just 2 years before he died, he proposed the Darcy's law. Darcy's law is one of the very fundamental and important laws that govern the groundwater flow, as we all know. So let's see what Darcy has proposed. Darcy's law states that the discharge of a fluid through a porous medium is directly proportional to the hydraulic gradient and the cross-sectional area of flow, and it is also inversely proportional to the length of the flow path. As you can see over here in the mathematical equation of Darcy's law, Q is equal to negative sign K multiplied with A multiplied with dH upon dL. K is the hydraulic conductivity and A is the area of cross-section. dH upon dL is the hydraulic gradient. All of these multiplied together gives us the discharge rate, or in other words, the hydraulic discharge. You might wonder why there is a negative sign. Well, that is because the flow direction is always in the decreasing direction of the decreasing heads. So, as you can see over here in the diagram depicted, the difference in heads given by delta H, that is the difference in heads H1 and H2. You can see the area of cross section and the outflow, inflow, and the porous media that we are going to pack in, which will explain you in the experimental part. And without any delay, let's get into the experimental part.
So this is the setup for Darcy's law experiment, and as you see here, we have a PVC pipe which is filled with beach sand. Now, beach sand acts as the aquifer and is a porous medium which will allow the water to flow through from one point to the other.
These two measuring cylinders are used to measure the difference between the pressure heads, which gives us the hydraulic gradient. The overall setup is kept at an angle of 15 degrees, which is done by using two stands and two clamps.
Now, as we can see, there are two pipes, the inlet pipe and the outlet pipe. And if you can observe that, the inlet pipe has a much broader diameter than the outlet pipe. And this is to ensure that we have laminar flow.
Now we'll see the overall experiment and how it works.
Laminar flow is one of the requirements in Darcy's law. In laminar flow, the layers of the fluid are parallel to each other, and turbulent flow is when the layers are not parallel to each other. Laminar flow occurs when the velocity of the flow is relatively slow and friction is high. Here, the Reynolds number is less than 500. And turbulent flow occurs when the velocity of the flow is high and low friction. Laminar flow is one of the requirements in Darcy's law. In laminar flow, the layers of the fluid are parallel to each other. Here, the Reynolds number is greater than 2000. As Darcy's law is only applicable in laminar flow, we need to maintain it throughout the experiment. To ensure that the laminar flow is maintained, inflow velocity is low and the pressure inside the tube is high. Also, the outlet has smaller diameter than the inlet, ensuring low velocity and high pressure.
The criteria for Darcy's law is that the flow must be steady and the medium must be homogeneous and isotropic, supporting laminar flow, such as in the case of sand. The sand has moderate permeability and well-connected pore spaces that enables the water to flow consistently and predictably, preserving the line relationship between the hydraulic gradient and the flow rate essential to Darcy's law. However, material like gravels, where large pore spaces can lead to turbulent flow as it introduces complexities like vortices and eddies. Or clay, where extremely low permeability and complex flow processes like capillary action and diffusion often makes Darcy's law less reliable as flow rates are too low to measure accurately and the assumption of steady flow is not achieved. Therefore, we use sand because of its homogeneity and isotropy to ensure that the hydraulic properties are consistent, making it highly suitable for applications in Darcy's law.
Hydraulic gradient plays a crucial role in Darcy's law, describing the water flow through the porous media. It is essentially the slope of water table or the piezometric surface. It is the rate of change of hydraulic head per unit distance in the flow direction and is expressed as H1 minus H2 by L, where H1 and H2 are the hydraulic head at 2 points, while the L is the distance between the two hydraulic points. Significance in the Darcy's law. Darcy's law states that the flow rate of the water through the porous media is directly proportional to the hydraulic gradient and the cross-sectional area of flow path. The hydraulic gradient acts as a driving force for the groundwater flow. The hydraulic gradient determines the direction of the groundwater flow. Water flows from the area of higher hydraulic head to the areas of lower hydraulic head. The magnitude of the hydraulic gradient affects the velocity of groundwater flow. A steeper gradient generally leads to head flow velocity. A steeper gradient generally leads to higher flow velocities. The hydraulic gradient can influence the availability of groundwater. In the areas of higher hydraulic gradient, groundwater may be more readily available. The hydraulic gradient plays a crucial role in the transport of contaminants to groundwater. Contaminants tends to move in the direction of hydraulic gradient.
I will say application of Darcy's law. First, groundwater flow. It is mostly used for estimation of groundwater movement through aquifers and well hydraulics and drawdown analysis. Second, petroleum engineering, modeling oil, gas and water flow in reservoir and anion soil recovery techniques. Third, soil science, infiltration studies and irrigation management and contaminant transport in soil. Fourth, civil engineering, seepage analysis in earth dams and retaining walls and design of subsurface drainage system. The last one, environmental engineering, land fields leachate modeling and groundwater protection and wastewater treatment system. Example, constructed wetlands.